Good morning, everyone. So, the next topic we're going to talk about is rates of change. And, well, basically, rates of change, you're observing how two variables change at the same time, or how does one change in relation to the other one. So, for example, if you're moving, if you're walking, you will be traveling through a certain distance, and that's going to take you some time. So when you calculate distance over time, you get what we call speed. Here it's a speed because you don't care about direction. This is a rate of change. That's a rate of change of position over time, right? Let's say that, I don't know, you look in the street, there is a pipe, they're making some work there, and there's some leaks, some water leaking from that pipe. How could you calculate the rate of change of leak, of water leak? Well, there are different ways you could describe this, call this flow rate. And what would a flow rate be? Well, it's how much matter is leaking or moving or passing through a certain point per time. So if you consider mass, you could have, I don't know, kilograms per second, kilograms per minute, kilograms per hour, depends on how large this flow rate is. Now you may also use volume, that's actually more common. So how many cubic meters are leaking per time? And remember that you can relate those two. If you give one, you can find the other one given the density of water. So if you remember, density is mass over volume. This is mass, this is volume. So if you use this relation, you can get from one flow rate to the other one. So from one rate of change to another one. Now let's say that you're traveling with your family after the coronavirus lockdown is over. So let's say that you're traveling with your family and you're going to a nearby city, right? If I make a graph of your position over time, it would be quite difficult for you to keep what we call a constant speed, because you walk a bit and then there is a traffic light and then you have to stop for people to cross the zebra cross, and then, well, anyway, the thing is, someone stops and then you have to slow down, and then there's an old lady crossing the street, and then you go into the highway, you can accelerate. So basically your displacement, it doesn't change like linearly as we're used, and then you stop, let's say. So this could be, for example, you accelerate and then you reach a certain velocity and then you have to stop in the traffic light and then you accelerate again, there's a cat, and then there's an old lady, and then you stop, you've parked, you're done. So this, if you get this point and this point and you make your a triangle here, you could find an average speed, right? You find here that would be delta S, how much you have displaced, and here it would be delta T. So you could just do your average speed would be delta S over delta T. Now, the huge thing that we're going to do here with calculus, and the huge change, is that we will try to get this line to be at a point, to be a tangent to a point. So if we take those points and move them closer and closer together, this calculation will get to something very interesting that we'll discuss further on. But so far, it's a rate of change. So, a rate is a comparison between two quantities with different units, as we have described before. And when we're talking about our our rate of change, specifically our instantaneous rate of change, it's given by the gradient, okay, of the tangent to the line, or to the graph at that point. So if, let's say, this is some rate of change, okay, it doesn't matter what it is, I haven't put any of the x's here, but we have some variable changing here, some variable changing there. If I pick 2 points and I draw a line going through those 2 points, that would be what we call a chord. However, if this was a distance time graph, this chord would give us some speed. In this case, average speed, because we're taking 2 points, which, right, there will be some, it's an approximation. However, if you're able to get this point to be closer and closer and closer, there will be, well, there will be a point at which it's so close that you're basically, pretend this is tangent, now that it's basically tangent at that point. And when it's tangent at that point, that's gonna be instantaneous. Alright? Now, this is instantaneous rate of change, and this chord here is going to be our average rate of change. So when we take 2 points, there will be an average, and when we manage to get a tangent, that will give us an instantaneous rate of change. And the tangent here is basically the gradient at that point, right? So the proper definition, the gradient of the tangent, y equals f of x, at x equals a, so this would be point A, is the instantaneous rate of change in f of x with respect to x at that point. So let's take a look at one example. Let's say that we have this function here, which is a quadratic, a very simple one, just simply x squared. And we want to calculate, let's say we want to calculate the instantaneous rate of change. So this would be rate of change of x in terms of y, but let's just call this the tangent. Okay, so I want to calculate the tangent at point 1, 1. This is not up to scale, obviously. Now, how would we do that? Well, first, let's get a chord. So, if I pick another point here, what would be its coordinates? Okay, so let's say this is point x. Well, if my function is f of x equals x squared, whatever this x is, this will be x squared. And if I take a gradient here, I would have my chord. So what would be the equation of this chord? How do we get the gradient of this chord? Well, we can close a triangle here, right? And then delta y over delta x. So delta y here is going to be x squared. How much have I displaced in y? Well, how much is this length? Well, it's this minus this, right? So x squared minus 1 over delta x. So rise over run. What is this length here? Well, if this is x, this is 1, this is x minus 1. X minus 1. Right? So far so good. For any point that we pick in this equation, this is going to give us the gradient. We can get any point. For instance, let's say, just as an example, let's say that I get x equals 2. So what would be the chord if this point was 2 and 4, right? It would be another point in our quadratic. The gradient, just as an example, would be then 4 minus 1 over 2 minus 1. So that's simply 4 minus 1, 3, 2 minus 1, 1. So 3. That's quite simple so far, isn't it? So let's do a practical experiment here. Let's design a table and let's try out some values. So I'm going to call this point B just so we have some reference. Okay, so we're going to get the point X. We're going to have the coordinates of that point and we're going to calculate the gradient. We want to get what's going to be the tangent at this point. So we will get this closer and closer to our point 1, 1, so we can find out if that value is actually converging, if this gradient is converging to anything. For those of you who can see a bit ahead, what we're actually doing is a limit. But we'll discuss that later. Look, when, let's say we get x equals 5, what would be the coordinates of this point when x equals 5? Well, 5 and 5 squared. This function is x squared, so any point will be x and x squared. The gradient, if we calculate, if we use this equation here, so I'll do just a few because it's just labor intensive and you can just put in your calculator, so there's no point, and you can make this table in a spreadsheet as well, it's just easier. So the gradient would be 25 minus 1 over 5 minus 1. So this is 24 over 4, which is 6, right? So what I'm going to do here, I'll just add some points which I am going to use as reference. So if you observe, I'm getting closer to 1, but I'll never actually get to it. So let's do 1.01 and 1.001, which should be close enough, right? So if you keep doing this, you would find then the points. This would be 3 and 9, and then remember that you can pause this video and try it yourself and find the gradient and try and answer what is this tending towards to. So when you go get x closer to 1, where's this gradient getting towards? So this is 2, 4. This is going to be 1.5 and 2.25. Next one, 1.1, 1.21, and I have some problems with space here, right? 1.01, 1.0201, and the last one here is going to be 1.001, which is this point, and 1.002001. Alright, so if you work those out, I will not calculate all of those because it would just be boring, but you can just put those in a spreadsheet, or you can use your calculator. So you would get values going down. So this would be 4, and this one 4 minus 1, 2 minus 1, that would be 3, and then this would be 2.5, 2.1, 2.01, and this last one would be 2.001. And any ideas where this is going towards? 2, right? So we can say that the instantaneous rate of change at point 1, 1 for the function f of x equals x squared is 2, right? And what do I mean by instantaneous rate of change? Well, that's our gradient, which is our tangent. So we have found the gradient of the tangent line at that point. Now, interestingly, some of you might not have realized, but we could have made our calculations much simpler. And you guys ask me sometimes, oh, why do I need algebra? Well, take a look at what we have here. We can actually simplify this to a much, much simpler calculation. Right? If you look at the numbers, it kind of shows, but if you haven't noticed, x squared minus 1 is something special. That's x squared minus 1 squared, which is a difference of squares. So x minus 1, x plus 1. And now since we're dividing this by x minus 1, we can get rid of them, right? Obviously, when we get rid of them, we have to remember that x should be different than 1, because we cannot divide this by 1, right? By 0. If we put x as 1 here, we would have a 0 denominator, so x has to be different than 1. That's why we're taking a limit. What we have done here, we have done the limit of this when x was going towards 1. And in this case, we came from the positive side. If we wanted to check if this limit exists, we would have to approach from the left as well. But in this case, it would work. Now, if you simplify, you would realize that this is simply x plus 1. So this is the same thing as limit of x going towards 1, x plus 1. And then this is constant, and this is simply x. So when x goes towards 1, x plus 1 will go towards 2. And that's done.